Alright, so we're going to go over some steps we can use when we're doing U-substitution. This will be for indefinite integrals. Then we're going to go over 3 examples in the slides, and you can see the solutions in the slides as well on Blackboard. So step 1 when doing a U-substitution is to find U. So remember from class we had 2 options for this, or guidelines. Number 1 was to find a function U such that its derivative, u prime, is also inside the integral. So that means we have to remember a ton of different derivatives and integrals. So for example, if I think u might be sine x, then I need to check that cosine x is also sitting in this integral somewhere in order for that to be my u. Other ones that we've seen already, u as square root x, du as 1/2 x to the negative 1/2, or 1/2 1 over root x. Don't forget your dx. So we saw that. Pretty much anything you could think of that we've done with derivatives could be somehow in there. So that's one way to do it. Another thing is to just look at your integral and pick whatever function is inside another function. So we might have something like sine x all being squared cos x dx, and you might look at that immediately and say, oh, well, sine x is inside, that means that should be my u. And it just so happens that the derivative of sine is cosine, and that's also inside the integral. So lots of options here. Another example that was similar to one in the worksheet, we had 4x plus 7 to the 5th. And again, as we stated in class, you could just multiply out this 4x plus 7 to the 5th, and you'd have a giant polynomial, and you could just integrate each term. Or you could say, well, I'm just going to pick whatever's inside, and I will see that I get something that isn't too bad for my u. Okay, so that's our find u, find du. So once we've picked u, we then want to calculate du, as you've seen a few examples of. And don't forget the notation. So when we're doing du, if for example we have in terms of x, we cannot forget this dx. It's going to be very important for us going forward. Okay, then we substitute. So that means everywhere there was x's, we should put u's, or if we're doing t's, whatever it is, but we're going to use u almost all the time for our substituting variable. So we want to substitute all into u's, no more original variable. Then we should have an integral that is easier for us to handle. We then integrate it. Don't forget your plus c. And after that, we should end up with some function of u plus c, but we want the original variable, so we substitute back in. All right? So that's the general gist of it, and we're going to see some examples. Okay, so these are complicated looking, but you'll see that once you get the hang of u-sub, they're not too bad. So let's start number 1, find u. So I'm going to look at this and say, well, I don't necessarily see anything in its derivative maybe, so I'm just going to go with pick whatever's inside another function. So u equals 7 plus tan t, because that's inside the 8th root. Okay, then step 2 is du is secant squared t dt. Okay, so at this point I say, is that in there? And sometimes you have to do a little algebra trig to get things to look the right way, but it is, if you notice, that that's really 1 over cosine squared t dt. And now I actually do see a cosine squared on the bottom, and I've got my derivative in there. Okay, so then let's substitute. So that's the integral. All right, so on the bottom, that cos squared t on the bottom, dt, all becomes du, right? So then that is this dt cos squared t becomes just du, okay? Then we've got this 7 plus tan t becomes just the u. So I have u under here, and then I have the 8th root. Okay, so let's rewrite that integral, and I'm actually going to simplify this a little bit for myself. Du over u to the 1/8, which actually I can rewrite as u to the negative 1/8 du. Okay, so step 4, I'm all u's now, so step 4 is integrate, and I can integrate this. That's u, I add 1 to the power, and then I divide by 7/8, but remember, you could just flip that up to 8/7 plus c, and we substitute back into t's because that was our original variable, and we're done. All right, let's try another one. Okay, so let's try to find our u. U is equal to, okay, so we look at this and I say, oh, well, sine's derivative is cosine, so that could be an option. But then I say, well, cosine's in another function, so why don't we pick that one? Cosine 36x du is equal to, so the derivative of cosine is negative sine, but remember, this is actually chain rule, so then I would multiply by the derivative of the inside, which is just 36. Okay. So that was 1 and 2. I forget to accidentally separate those into different pieces. So then 3 would be to substitute, but we should probably take a second first, because we'll notice that in the original function there is no negative and there is no 36 outside any of the trig. So the way we deal with this is anything extra on the right hand side we just divide over. So that's du negative over 36, all right, equals sine 36x dx. Now this and this can get substituted out for just that. So let's do the substitution. So that becomes negative du over 36. And then I've got 1 over 1 plus u squared. Okay, I'm in all x's, that's great. I am going to actually take out the constant. Alright, and then I'm going to integrate. Okay, so this is just one we have to remember. The antiderivative of 1 over 1 plus u squared, or if in your brain it's helpful to remember to put it into x's right now just to think about it, should register as arctan, or tan inverse. Alright, and then we substitute back. Tan inverse of, cosine 36x plus c. Alright, so let's try one more. Okay, so again, we start, let's find our u. So I'm just going to go straight to, is there a function plugged into another one? Well, I see that natural log of 36x is inside sine, so that's a good place to start. Well, let's test it by doing du. So that's 1 over 36x times 36. So that's an application of the chain rule, but it actually just simplifies to 1 over x. Don't forget your dx. And actually, we see that here. There's an x on the bottom, dx. Okay, that's x on the bottom, dx. That should just become du. So when we substitute, we get sine of u. The x dx, the 1 over x dx becomes du, and pretty simple integral. So let's do it. Right? The antiderivative of sine would be, well, we know it's cosine to get from sine to cosine, right? But remember, the derivative of cosine is negative sine. I do not have a negative in this integral, which means I had to have had a negative on the first one. So that's one way to kind of remember them, is just do the derivative backwards. You should be able to get straight to the function you had in the integral. plus c. All right. Okay, let's substitute back in. Negative cosine of natural log 36x plus c. And there you go. So, let's review. Just did 3 examples where we found u, and by doing that, we looked at 2 things. I think using both of those together is really good. And you could start with either of these. Either pick a function u that's inside another, perfectly fine way to start. Then your check can be, is the derivative of that thing I just picked inside the integral as well? And remember, that can be up to a constant. It's okay if I have the derivative, I just don't have a multiple of 3. We can deal with that. Okay, number 2 is find du, so do the derivative. 3 is substitute, 4 is integrate, don't forget your plus c, and 5 is substitute back. So I have the section 5.5 problems and solutions up, so please check those out, go through them, practice, 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 work on your homework, and let me know if you have any issues. I'll see you in class.